All right, so first thing, just cleaning up one of the concepts we didn't really get to last week, which is called the biconditional statement. So last week we talked all about conditional statements and the related conditional statements and finding truth values and all that. The biconditional statement is sort of like another related conditional statement. And so we use a biconditional statement when both the original conditional statement is true and the converse is true. Remember, the converse is when you switch the order. So if you have like, um, conditional statement and then you write the converse, but both of those things are true, you can actually combine those two statements to create a single statement called the biconditional. Really what it means is it sort of goes both directions. We talked a lot last week about how biconditional statements have a direction. If the hypothesis is true, then the conclusion also has to be true. But if it works both ways, then we can actually make that into a biconditional statement. And they're going to be used a lot when we write definitions. So when we define something, it's nice to have it biconditional because you don't need to write down these notes unless there's things that you want to write down about them. A biconditional statement is really useful for definitions because you can say if this geometric thing, if we call it this name, then it has these properties. But we also want that to be true, that if it has these properties, then we can call it these names. We want it to work both directions when we're talking about a definition. And we'll see that on the next slide here. Okay, so we have a conditional statement, which seems easy enough to understand. If an angle is a right angle, then that angle measures 90 degrees. Basic conditional statement. We could almost think of this as a sort of definition, as part of a definition of what a right angle is. And it's definitely true, right? If something is a right angle, it's 90 degrees. That's the way we think about right angles. But the converse of that statement, if we switch the hypothesis and the conclusion, the converse of that is also true. If an angle measures 90 degrees, then it's a right angle. So you can see how it's working both directions. It doesn't matter which one is the hypothesis and which one's the conclusion. Either order, we're going to have a true statement here. And so this is where we can use what's called a biconditional statement. It's going to sound weird, but this is the way we always write it. And then in symbols, a biconditional statement is an arrow with both directions, meaning that it could be P, if P then Q, or if Q then P. It can go both ways. So here's the biconditional form of that. An angle is a right angle if and only if it measures 90 degrees. Those words in the middle there are the key to it being a biconditional statement. If and only if. Those are the ways that you'll know that it's being written as a biconditional statement instead of a regular conditional statement. There's no if and then, it just has this if and only if as a connector between them. Yeah, so a good question. Sometimes you can write conditional statements that the converse isn't true. You could say something like, let's see, something where the converse would not be true. Oh, so like if an animal is a cat, then it is a mammal. If you switch that, if you write the converse of that, if an animal is a mammal, then it's a cat. That's not always true, right? The original one was true. Cats are always mammals, but mammals are not always cats. So it does matter the order, but sometimes it doesn't matter, like this. And most in particular, when we're trying to define something, we're trying to write a definition, those are where we're going to use biconditional statements as definitions. All right, that's just a really quick thing, and we'll do one more example of it right here. So I'm going to clear what I have. Yeah, biconditionals are used when we write definitions. That's really where we're going to see them. All right, so let's write a biconditional statement for the definition of supplementary angles. I'm going to get it started for you. So I have a blank, and then an if and only if, and then another blank. We got to think what we know about supplementary angles, right? They have to add to 180. That's kind of their main idea, but I'm going to go ahead and get it started. So two angles are supplementary if and only if, what do we need to write there on the end? So two angles are supplementary if and only if this. Any thoughts? You can put it in the chat or feel free to say it if you'd rather do it that way.
They add to 180.
They add to 180. I want to be a little more like precise in my language, but that's absolutely all I'm really looking to say, right? Two angles are supplementary if and only if their measures add to 180 degrees. This is a definition. This is us defining supplementary angles using a biconditional statement so that we know if two angles are supplementary, then we know their measures are add to 180, but also it has to work the other way. If two angles measures add to 180, then they're supplementary. Has to work both ways for it to be a good definition. If it doesn't work both ways, if we're not specific enough, then it's not a great biconditional statement. But this one works, it's fine. We could maybe be a little more precise and clean up things like their, add to. There's always some more specific language that we could probably use, but we get the point of what this is saying. This is a basic biconditional statement for the definition of what supplementary angles are. All right, we'll come back to biconditionals when we start doing more definitions and proving more things. But just wanted to make sure we understood what a biconditional statement was. All right, now we're going to go ahead and move on to something both familiar, probably, and slightly unfamiliar. We're going to talk about proofs. The part that's going to be familiar is we're going to be doing a lot of algebra. We're going to be solving algebraic equations, but what we're going to be doing is we're going to be writing justifications for each step. So in algebra, you probably learned a few properties that you're allowed to use with equations. Like you can add something to both sides of the equation and it's still equal, or you can multiply to both sides of the equation and it's still equal, those sort of things. Those are some properties that equality has that allows us to actually come up with solutions. And so we're going to use those to write kind of justifications as we go. And this is going to introduce us to this idea of proof. So what is it? A proof is an argument that uses logic, definitions, properties, and anything that was previously proven to show that we have some conclusion which is true. I'm using the word conclusion there in the same manner that we would have in a conditional statement. So when we're writing a proof, we have some sort of a hypothesis, some initial given information, and we're trying to show that based on that hypothesis, our conclusion is true. And the connector between those things is going to be our logic. Thank you for letting me know. Our logic, definitions, properties, and things we go. We're going to start off with something pretty familiar to ourselves and kind of work into the new stuff, the geometry. So proof is really the reason that we're taking this class, geometry. That's going to be one of our main topics that's going to extend sort of throughout most of this semester and a lot of next semester. We'll be doing proofs kind of regularly. But what we're going to do is we're going to start with something that's hopefully familiar, some algebra skills, in particular solving equations. Okay. So for a proof to be complete, and this is going to seem like overkill a lot of times, you have to have a lot of stuff in there, I'll say. You want to make sure that it follows a logical order. It gets us from our hypothesis, which is our starting information, to our conclusion with a justification for every step. We're saying, why did we do this? Why did you add, or why are you allowed to add to both sides of each equation? Why are you allowed to make this statement? You're writing a justification, and that might be a definition or a property or something else. We'll see, there are many things there were. And it's really important that we're not skipping over anything. We're leaving no No stone unturned is what's said here, but we're not leaving anything to the imagination of the reader of a proof. It's all there, nothing is skipped, nothing is glossed over, and everything is justified. It's going to seem, at least in the beginning, like we're doing a little bit too much, being a little bit too precise, but that's what proof is really all about, is that precision. So this last thing means that every detail is addressed. All right. What do we need for algebraic proof? So for algebraic proofs, we need to understand and remember what are called the properties of equality. So there's sort of the rules that govern the equal sign, right? The equal symbol. What are we allowed to do when we have an equation? And there's a few properties that we'll need to know what they are. And there's one that's not technically a property of equality. Okay. So this one here, this one I'm going to put on the side here. This one technically is not a property of equality. This is the distributive property. Remember, it tells us that if we have a number on the outside of some parentheses like this, we can distribute it, we can multiply it into everything. We use the distributive property sometimes when we're solving equations, so it's important to know. This is not technically a property of equality. This is technically a property of multiplication. Multiplication can be distributed across addition or subtraction in this way. The rest of them are going to be properties of equality. Again, you don't necessarily have to write these down. You can find them in the textbook in this section too, or they'll be here on these notes. But if this is something you want to have, it's fine. So the first one is the addition property of equality. Really, the addition property of equality, the only thing that it says is if you have some true equation, then you can add the same thing to both sides. So in this case, we added c to both sides. That's fine. As long as we add the same thing on both sides, that new equation will also be true. Notice it's written as a conditional statement. If this is true, then this other thing has to be true. In that same vein, we have something called the subtraction property of equality. If a is equal to b, well, then we're allowed to subtract the same thing on both sides of that equation. A minus c will have to also be equal to b minus c. If that initial statement was true, then the conclusion here would have to be true. Basically, we're allowed to subtract the same quantity on both sides of an equation. You've gone through these, you learned these properties, maybe not the specific names when you were solving equations. Multiplication property of equality, same idea, same thing. We're allowed to start with a true equation, we're allowed to multiply both sides by the same number. So if a is equal to b, then if we multiply those both by c, they're still going to be equal. You might have guessed the next one, the division property. Same thing. If we have a true equation and it's very important, c can't be 0, then we can divide both sides by c. Why can't c be 0 for this property? Why is that important? Any thoughts? So hopefully you remember that dividing by 0 is a problem in math. We can't take something and divide it into 0 pieces, right? So that's kind of a mathematical anomaly, not something that we're allowed to do. It's okay for all these other ones. We can add 0, subtract 0, multiply 0, but we can't divide by 0. So those are the basic ones. These are the ones that are most commonly used when we're going to be trying to solve an equation. We're going to have to add something to both sides of the equation. We're going to have to subtract something from both sides of the equation. We're going to have to multiply or divide, right? Those are the most common things that we're going to have to do regularly. Just trying to keep track of my time. Now, there's a few other technical properties that we also need to remember that may come up here and there. The first one is called the reflexive property of equality. That just means that everything is always equal to itself. I like to think about it as it's looking in the mirror. When you look at the mirror, you're seeing yourself. You guys are equal to each other. You're a reflection of each other. So everything is always equal to itself. This is kind of a technical property that will come up in in geometric proofs later on, it's something to keep in mind. In particular, when we're trying to prove whether or not two triangles are congruent, it's possible that they share a side. And so since they share a side and that side is part of both triangles, they'll be congruent. But that's really technical and we'll get into that later on. The next thing is called the symmetric property of equality. Basically means that it doesn't matter which side of the equation things are on, we can flip-flop those. If A is equal to B, then B is equal to A. That's useful like when we're solving an equation, we get 6 is equal to X. That's the same thing as saying that X is equal to 6, right? So we might flip that around using the symmetric property of equality. Again, pretty technical step, but does come up. Next one here is called the transitive property of equality. This one's also very useful. We'll use transitive property a fair amount. So if A is equal to B and B is equal to C, then A is equal to C. This allows us to sort of set up a chain of equality. We can say, okay, this is equal to this thing, that is equal to that, that is equal to some other thing, and you can create a chain saying that the first thing is equal to the last thing. That's called the transitive property. It's pretty useful. Again, we'll use it quite a lot when we're talking about like angles or segments. If this angle is equal to this angle and that equals to another one, then we can kind of shortcut it. So transitive property will also be used a fair amount in geometric proofs. Another really useful one is called the substitution property. Substitution property basically says that if we have two things that are equal, well, then in any equation or expression, we can substitute one of those things for the other one. So if A and B are equal, then anywhere we have A, we can substitute B for it. Or the other way around. If we have B anywhere, we could replace it with A also. Substitution property is very powerful, particularly when we're trying to figure out particular segment lengths and particular angle lengths. We'll need to be substituting values in. All right, sorry, I'll go back to that. These are really the properties that we're going to be working with today. We're not going to go kind of beyond that. Eventually, we'll add some more of our geometric properties about midpoints and angles and things like that. But for right now, just knowing these properties are going to be what we need to do. All right, so how does this actually look? So let's say we're starting off with an equation like this. Negative 13 is equal to 3n plus 5. So this is our given information. We could think of it as our hypothesis. And what we're trying to prove is what is n equal to? Our conclusion is n is equal to something, and we're trying to show what it's equal to. So to solve this equation, first step, I would just get rid of the 5 on each side, right? So subtracting 5. That leaves us with this. Negative 18 is equal to 3n. Then at this stage, go ahead and divide both sides by 3, right? So we divide by 3, and we figure out that n, which is on the right side, is equal to negative 6. So that's the way we know how to do it. But this isn't a proof. This is just us solving an equation. What we would really like is to write some justifications next to each of these steps. So I'm going to do that. So this is our given equation. So we're starting off with, we also might call this our hypothesis. Then we subtracted 5 from each side of our equation. That is something that we can do based on the subtraction property of equality. We're allowed to subtract the same thing on both sides of our equation. So there we go. And then we did this. So now the question is, how did we get from this step where we were subtracting down to this one? Sometimes people use this term. They say, okay, all we did here to go from subtracting to this is we simplified. We actually, all we really did was did negative 13 minus 5, right? Some people write simplify, and I'm okay if you write simplify, or some other people might say combining like terms or something like that. I'm going to call it something different. I'm going to call it substitution. Essentially, we substituted negative 18 for these numbers right here, right? For negative 13 minus 5. We substituted equal quantities. So instead of having the subtraction, we substituted what it was equal to. I'm okay if you write simplify. Some people might want you to be more specific and say that it's the substitution property of equality. Doesn't matter to me. Either way is going to be okay. I will use both. All right, now we're dividing by 3. We're dividing on both sides, which is obviously the division property of equality. That's what allows us to divide both sides of our equation. And then we get negative 6n. We also want to justify that step. We divided, so we either simplified our division, or we substituted an equal value. So we took negative 18 divided by 3, substituted it for negative 6, which is what it was equal to. Pretty specific, but I'm okay with one either way. All right. So what we have here is every step has a reason. We've left nothing to the imagination. We've shown every step and we've justified it with one of these properties of equality. That's what a proof really looks like. It's very detailed. And right now it seems overly simple because we're proving something really simple. We're proving a pretty basic equation, right? Once we start working with more complicated geometric ideas, it'll make more sense for us to be this specific. All right, I'm gonna go ahead and go from there. So here's an example. Let's do this one right here, and I'm gonna go through it. I'm just gonna kind of show what I would do for this one. A common way that we will do proofs is what's called a 2-column proof. So we'll have all of our work and steps on the left side, and on the right side, we'll have kind of all of our reasons or justifications. So I'm going to write this here. We call this our statement or the work. And then over on the other side, we have our justifications or reasons. This is where we're going to put like our properties of equality and stuff. So the very first thing we have here is the given equation, or our hypothesis. So we always start off with our given equation, and then we kind of work from there and see what we're doing to it. So what do we need to do to this equation? We need to get rid of this 3, right? So we need to add 3 to both sides. Yep. And what property of equality allows us to do that? Well, seems like a lot of work, but it is the addition property of equality. I'm going to shortcut these properties and just call them like addition property rather than talk about addition property of equality. But it's important right now for us to make sure we're clear in what we're doing. All right, so now what does our equation become? Our equation becomes 5x equals 5x equals negative 7 plus 3 is negative 4. That's a good question. Thank you for pointing that out, because that is totally not what I did. Let's just go ahead and pretend that I did it right. For some reason, I was reading this totally wrong. Okay, let's do it correctly. Thank you for catching it. Minus 3. Because we are not going to be adding 3 to get rid of that. We are going to be subtracting to get rid of that, which leaves us with 5x equals negative 10. That is our resulting equation there, right? And we want to write our justifications over here. So this first one was the substitution subtraction property of equality. Again, you can shortcut that. I'm pretty okay with you just writing subtraction property, or even later on, you know, even shorter than that. We kind of get the point. But for now, let's just be specific. And then I reduce that down. I combine stuff together. So I either can say that I simplified, or I use the substitution property of equality. Again, I don't care too much what was going on there. Yeah, you guys already know the answer pretty quickly because this is a fairly simple equation. The last step is to divide by 5, right? And that obviously is the division property when we're dividing. Dividing both sides, division property of equality. And then what is our answer at the end? We end up with -2. Yep. X equals -2. Again, you can either say that you simplified or you substituted an equal value. I'm not going to be very picky with this. I'm probably going to use both of them here and there. I'm just being really specific right now about what it is. So doesn't matter right this second. You can call it simplified, you can call substitution property. I just want to make sure we know both of those are options. So there's our answer. And this right here would be our conclusion. So if we were to write this out, this proof out as a conditional statement, so going back to what we were doing before, we could write this entire proof out as a conditional statement, or at least the what we proved as a conditional statement. So if 5x plus 3 equals -7, then x equals -2. So we could write this out as a conditional statement of our proof, where what we started with, our given beginning, is the hypothesis, and what we ended at was our conclusion. That's really what a proof is. It's a logical argument of some conditional statement. You start with your hypothesis, and then you show through very justified steps that you can reach your conclusion from that starting information. There's a connection between what we did and what we're doing here. I want to make sure you understand that. All right, I'm going to go ahead and clear this and put one more example up for you guys to do. We are running low on time. I know some people asked if I had some time to do homework problems. I don't think I'm going to have time right now, but I definitely will tomorrow. There's not that much to get through tomorrow, so we will have time. We can start with that tomorrow, okay? Some of the homework problems. I'm going to clear this and give you guys a chance to do the next one. It's also called example 1 for some reason, but here's a problem. I want you to try to solve it and write your justifications on the side, okay? So take your time, try to work through this one. Do the 2-column structure that I was showing. Keep it nice and organized. I'm going to add one more thing to this one that I didn't say last time. A lot of times people will kind of really separate things out and number each step just so that it's a lot easier to kind of follow and see which goes with which. So I'm actually going to give myself some horizontal lines here. I don't know how many I need. Hopefully this is going to cover enough, but we'll see. So a lot of times you will see each step numbered for easy reference. And we're always going to have whatever is given to us in the beginning. We'll either use given or given equation or hypothesis, whatever. That's a common thing that we'll see, that we always start with whatever has been given to us. All right, what's the first step you guys want to do on this one? Couple options. I could either cancel out this 1/2 or I could distribute it. Either one is fine. I'm going to use the distributive property since I'm allowed to, right? So I'm going to multiply that in. But I could also just multiply both sides by 2 to get rid of it. So that would become 2x minus 3 equals -7. And that is our distributive property. Again, I'm shortcutting it now because I'm writing it out, but it's okay. Now we have a pretty easy equation. I'm going to go ahead and add 3 to both sides of this. So that is our addition property. I am supposed to add, right? Yeah, addition property. Okay, what do we get here? That's going to be 2x equals -4. We simplified. Or you could say it's a substitution property. Either one of those is fine. And last thing is I'm going to go ahead and divide both sides by 2. So that's our division property. And the result, x is equal to -2. Is that the same answer we got last time? Yeah. It's okay. What do we got here? So we divided. We could either say it's simplify, or again, we could use the substitution property. All right, it's 11:04. So that's our time. I'm gonna go ahead and stop right there. I'll start tomorrow with some homework questions. If you have something pressing that you have a question about, send me an email. Otherwise, I'll see you guys tomorrow. Bye. Uh, yes, I will get to that as soon as I can. A lot of things are great right now.